So you want to be an Android reverse engineer. I'm Justin, a reverse engineer at Trux, and the purpose of this series of video is to be a crash course into reversing modern Android applications. So when you first start your Android reverse engineering career, you must first understand the mobile threat landscape. What is that? Well, it's basically any malware affecting mobile. The first thing you need to know is that it's growing. It's growing significantly faster than things like Windows. Last year it grew by like 30%, and phishing alone was apparently three times that of last or 2022. The reason for its growth is that Android is simply much more accessible than, say, Windows. There's 3 billion Android users worldwide, and all of those users are now using their mobile devices for things like personal information, banking, subscriptions, paying for things with credit cards, texting their friends. And all of them are, of course, susceptible to malware attacks or being targeted for specific espionage, like influencing an election. To top it all off, these users may not always be following the best security practices. They may be installing apps they shouldn't, clicking on links they shouldn't, or trusting something simply because it looks like their bank. You may think that mobile devices have a very strict sandbox that all apps must follow, and this is true. However, in practice, that sandbox is just not sufficient at actually stopping attacks. Um, root or what I would call non-APK binary attacks are extremely rare in Android. And the reason for that is because OEMs are much better at securing their devices. And of course, AOSP as a whole has more security features now more than ever. So, very happy to say that very rarely will you see some sort of grand privilege escalation exploit. So, in practice, what this means is that almost all malware is going to live within the confines of the application's sandbox. What can you do within the sandbox? Well, you could do phishing, which is basically impersonating something like a bank or otherwise stealing credentials. You could do toll fraud, which is signing up the user to a subscription without their explicit consent. You could be maskware, which is an app that looks like something, but in reality, it's something else. You could be a remote access Trojan, which is typically going to be ALNY. That would allow you to like share the screen, perform clicks, all sorts of nasty behavior. You could be a proxy Trojan, which is basically an app that will forward traffic using whatever network you're connected to. That's actually very valuable for things like botnets that need to spread out their IPs. You could be a part of a pig butchering scam. So maybe as part of a pig butchering scam, at the end, you have the user install an app, which they then say invest in some fake investment. You could be click fraud. So clicking on advertisements in the background to generate artificial clicks. You could be spam, simply, spamming the user with send text message. You could be SMS fraud, which is sending text messages to a premium SMS number. Similar, you could be call fraud, which would be calling a premium number, although that's kind of not as subtle. And of course, you could be everyone's favorite adware, simply spamming ads in with or spamming the user with ads in a way that is very disruptive. So, to facilitate these kind of attacks, you will find that in practice, almost all Android malware is going to look legitimate, at least at first glance, right? And the reason for that is because you actually need the user to install the APK, run it, and grant any permissions. And if you want your app on like the Play Store, then you're going to need to actually make sure you have something there to bypass any sort of review process. So, with that, let's actually start talking about some concepts, shall we? So, to start with, I want everyone to know what the entry points within Android are. And to do that, you'll need to somewhat understand the activity lifecycle. The activity lifecycle will actually look very similar to the lifecycle shared by an application or service. The activity lifecycle will mean that your entry point will typically be on create. That's what's called when activity is first launched. Application has a similar call to on create when the application or process is first created. Services work like activities, except they don't have any sort of UI. They're made to run in the background, but just like the activities, they'll have an on create and also stuff like on start command. Broadcast receivers are an entry point in that if you send a broadcast originating either from within the app itself or externally, like receive boot completed, then that can serve as an entry point. Content providers are made to process content URIs to basically allow other apps to gain access to files or other resources. So you can actually embed malicious content in there, and in that way, a content provider can actually be a malicious entry point. So the reason why you need to know its entry points is because if you want to know what to actually look for, that's where the app starts. There's no like main function. It's going to be one of these classes being called by the lifecycle. The second key point of reversing Android applications is that there's actually multiple different frameworks you can use to build an Android app. The most common is the legacy system known as XML views. Those are made using XML layouts, which are found within the resources of the application. It's relatively easy to reverse those compared to other frameworks. So um, that's typically what you would see in like an existing tutorial on Android reverse engineering. The replacement for XML views is known as Jetpack Compose. Jetpack Compose ships with its own like drawing library, which means it can be significantly better at obfuscating and minifying itself. That makes it much harder to reverse than, say, XML views, which has those hardline XML views and other dependencies. We'll actually look into Compose today, so just try to keep it at the back of your mind for now. The next one is React Native, which is basically React except done in Android. React Native is written in JavaScript, but it's actually compiled into a form known as the Hermes bytecode format. And Hermes can be a little bit difficult to reverse. So that can prove to be a challenge. Cordova is basically statically serving a website from the application itself. You might see that when someone wants to use an actual web framework to make their app. Unity is a game engine. The developers will code their code using C sharp. Um, you don't actually reverse that using like something like .peak. You reverse it using Girja because Unity actually ahead of time compiles all of their .NET code into a form known as IL2 CPP. Flutter is built using Dart. Dart is ahead of time compiled into a special form, which is what you'd see in a Flutter app. Unfortunately, that is native code, so it tends to be one of the hardest to reverse. The two in bolded, XML views and compose, are both made in Java. So those ones just in general tend to be the easiest to reverse. They're also the most common, so they should be where your focus is. All right. Now we talk about frameworks. Let's actually talk about the permissions model. So Android apps don't actually have much for out of box privileges. They have to request them by declaring them in the manifest. Some permissions are granted automatically simply by putting them in the manifest, but others are considered dangerous. Dangerous permissions would include stuff like bind accessibility service, read SMS, send SMS, and call phone. Bind notification listener is not actually one of the dangerous ones, but in practice, it's pretty dangerous. So, with a dangerous permission like read SMS, you would have to explicitly have a pop up within the app that would then allow the user to grant that permission. So, you've probably heard me talk about the sandbox already, but what exactly is that and why is that important to you as an Android reverse engineer? Well, at a top level view, the application sandbox is mostly built on Linux features. So each app is its own user that owns its own files, and those users will be persistent across app launches. That just automatically leaves a good barrier between, say, accidentally disclosing information to another app. But it's not good enough. Like, say, you accidentally make a permission for a file 777. Beyond that, each app has its own storage. So there's not like a central storage location for everything. And that is more so true after scope storage was implemented. Apps are not allowed to or share memory with one another. They have to use a system known as Binder for passing messages to one another. They don't technically have to use Binder to pass messages. You could do something like open a socket, but in practice, almost all interprocess communication in Android is going to be done through Binder, and we'll look at how that's done in just a second. If you may have remembered, I just talked about how you might accidentally make a file 777 and how do you prevent accidental disclosure that way? Well, SE Linux or mandatory access control can help us accomplish that. So the way that works is the domain of an app would be something like untrusted app, and they'll use categories to prevent disclosure between different applications. That's a very top level view of it. You don't really need to know how SE Linux works from the reverse engineer standpoint, but you should know it's there and a very core security feature of Android. So that about wraps up the application sandbox. Let's now talk about the system server. The system server is a collection of services that run on UID 1000. You'll typically see that called the system if you run PS-A. That will include things like the telephony manager, location manager, activity manager, and of course the package manager. There's so many services, far too many to list here, but if it's something you call by context.get system service, it's most likely going to be talking to something through the system server. You should also know what the Zygote is. The Zygote isn't really part of the sandbox, but it's an important fundamental for learning why Android apps are the way they are. So when you launch an Android application, it's going to fork the Zygote. So your app is just a simple fork of the Zygote. And it's this is done for optimization because that Zygote is going to contain preloaded system libraries, such as what you use to talk with the telephony manager. And it's also going to contain classic UI implementations. So all of the data used in XML views, or rather implementations used for XML views, would be in the Zygote. That's all defined in AOSP. So you're not actually going to see that code within your app. Just to demonstrate that, let's see what a call to a system server service looks like. So at the top is your app here. That's your UID, whatever it is. Here's your app code and here's the Zygote code. And let's say you call something like context.get system server service, telephony manager, and you cast it to telephony manager, and you call something like get sim operator code. Well, the actual implementation to get sim operator code will be in the Zygote code. And what the Zygote code is going to do is it is going to use Binder to talk to the telephony manager. So it's not actually um, you're not actually like directly calling the service. There's an extra step, and hopefully that point is made very clear by this. The system service would then check your app's permissions to make sure you can do whatever you just requested and then respond back. That would go back through Binder, back to your app into the Zygote code and be returned to your actual app code. This is very important for the RE because the code that does this is not actually in the APK. And this also applies to things like what actually calls on activity. Well, what calls on activity is something known as the activity thread, which is communicating to the activity manager in a way that's very similar to this. And that activity thread will then call your activities on create. And that code is not in the APK, so don't look for it. All right, so we've learned what the sandbox is. We've learned basics of Android apps. Let's look into how an APK is built. This is good context to have as an RE because it helps explain why code looks the way it does. So, the core build process of your code is that it will be controlled by a build system such as Gradle. And typically, you're going to use Android Studio for that, but that's not technically a requirement. The first step in the build process will be allowing any sort of compiler plugin to generate any code it wants, i.e., Compose has its own compiler plugin. After that's done, the code will then be compiled into the .class format. If you're a Java developer, you probably know what those are, but that's what's generated by things like Kotlin C and Java C. That is not the format that Android wants, though. Android wants a format known as Dexes. So the classes are then dexed using D8, which is the new dexer. The previous dexer used to be known as DX. Once that's done, that code is now ready to be used in the Android app, but if selected by the developer, they may do some additional obfuscation. One of those obfuscators that's shipped with Android Studio by default is known as R8. And R8 will minify the code, also perform extra features like inlining and creating or patterns known as lambda groups. That's probably just only getting to the start of what R8 does, but those are the most impactful things to an R8. The build process will then pack all your resources. This would include things like the Android manifest and resources. The resources will contain things like the layout that XMLs that you need for XML views. And the Android manifest is going to contain all the definitions for your activities, permissions, the name for those activities, and other information about an application that the system needs to actually run it. All of that data is then uh, packaged together and signed in a signature stored in the meta-inf and put into a zip file that we call the .apk or Android package. And that is what you, the reverse engineer, will be reversing. So within the APK, you would see those DEX files. And in most cases, that's what you would want to see there. But sometimes there'll also be stuff like native code or a certain asset file. Those will be in the APK as well. But most of the case, you're going to be looking at the DEXs. The dexes are in the Dalvik bytecode format, which I don't think actually has a public notation, but they can easily be converted back into dot classes. And the dot class format can be read in the form known as Smalley code. And Smalley is basically assembly, but for Java. The good news is the dot class files are actually relatively easy to decompile. So generally speaking, you should simply look at decompiled code. That's not always the case though. It is possible to generate code that doesn't decompile nicely. So sometimes you may need to read Smalley code. Don't feel intimidated by that. Smalley code's actually really easy to read. It's not like real assembly where there's complicated instructions. They're pretty self-explanatory. But just in most cases, use the decompiled code, and only if there's a major problem should you be switching to Smalley. All right, so we have gone over the basics of Android. We have learned what sandboxes. We see how the APK is built. Now, what do you need to know to actually reverse things? Well, um, I would recommend not just diving deep into an app. You should think like a malicious actor, and to think like a malicious actor, you need to know what kind of techniques a malicious actor might do. So I created what I'm going to call the core must know malicious evasion techniques, and these will typically be the things that you'll look for when reversing an Android app if you're trying to find malicious behavior. The first one is going to be encoding/decoding. That's going to include things like base64, JSON, other things. Base64 would probably be the one you'd actually see in this form, but there are alternatives like there's like a minified JSON format. And the reason why a malicious actor might do this is because if you encode a string as base64, well, now that string's not going to show up as a pure string when you run the virus tilde rule and look for strings, right? So very useful to evade detection. The second core must know feature is going to simply be encryption, and we'll look at what these calls look like in just a second. This will include things like AES, DS scissoring, or other special encryptions. And the reason why a malicious actor might do this is say to have a C2 and they base64 encoded it. Well, that's not good enough because we can just decode it. So let's also encrypt that C2 so that we can't just base64 decode it, but now we also have to decrypt it. And that's not always that easy to do because many times that key might be hidden or maybe it's dynamically retrieved. The next core must know technique is going to be known as reflection. And what reflection does is it allows you to reference a Java class or method by a string. And that's critical for malware because that means that that method and class are not referenced directly within the .dex. Um, and using reflection, you can actually invoke and create objects without actually leaving a static trace to those elements. You'll see reflection used a lot to hide code this way. For the most part, you would look for things like java.lang reflect, and we'll go into that in just a second. The next core must know technique is going to be JNI/NDK. So basically, just native code. A malicious actor might be using that as part or even their entire attack chain. Native tends to be a little bit more difficult to reverse in Java, so that's why it's used. The next the next core technique is known as dynamic code loading or DCL. What dynamic code loading does is it allows a application to remotely load code, either a DEX file or an ELF format shared object file, and then load that into the application and execute that code. Malware will do this because they don't want detection to see the code that they're trying to, run to perform their attack chain. If it's simply not in the app, then obviously you can't detect it. So typically, many times the DCL behavior will be cloaked somehow, so it only runs after a specific guardrail is passed. We'll see what DCL looks like in just a second. There's also packing. So packing is basically the same as DCL, but instead of getting your code remotely, you just have it within the app. Once again, that makes it a little bit more difficult if you're trying to analyze an APK in a purely stack sense because that code won't be there until you unpack it. Next core must know technique is going to just be various guardrail techniques. This would be things like locale, which you can use to infer what country you're in, sim info, which again you can use to infer what country you're in, GeoIP cloaking, which once again you can use to infer what country you're in. Time delay, like maybe you make an APK, but you set it to weaponize itself sometime in the future. Device architecture. Most Android emulators, or sorry, most Android devices are going to be ARM based. So if you're using like x86 or x64, you're probably an emulator. And so malware will many times use this as a guardrail to prevent the app from running on an emulator. Likewise, device model, anti-free checks, anti-root checks, and many more things will serve as those guardrails as well. So if the technique has an X, that means it's going to be something we're going to showcase in a sample app today, which we will get to after we're done talking about techniques. So I've described what those techniques are. How do you actually look for those within the app you're reversing? Well, when you think of malware, I would think of it this way. Malware has a collection of techniques, tactics, and procedures, right? What do those look like? Well, statically, they're going to look like one thing. Dynamically, they might look another way. And what behavior that technique actually showcases, like something you'd actually observe the application doing, may look different as well. And so, by thinking of how a single technique can look at differently, or how you can like look for that behavior in different ways, you can use this information to effectively reverse an application without having to do, very deep dives. So let's take a look here. Encoding. Well, if an app is doing encoding, it's probably going to be using Android.util.base64. There's other base64 libraries, but this is the most common. If you want to analyze that dynamically, you might hook dot the code of the same class. If you want to see what behavior this is, well, maybe if there's a base64 string being retrieved through an HTTP request, like maybe you have like a snort rule or something, you could then infer that there's probably some sort of base64 decoding going on. Next technique, encryption. Um, when malware uses encryption, they're probably going to use javax.crypto.cipher. That again, that's not guaranteed. They can implement their own, but in practice, they'll probably do this. And the way you might see that is you would see the cipher and a dot do final. So you could simply hook dot do final to actually decrypt the stuff dynamically by just dumping it out. And what behavior might this show? Well, if you find some content retrieved remotely, that content might have high entropy. Encrypted content tends to have a high entropy value. If you didn't know. Reflection. So reflection can be seen in a few ways, but typically you'll see java.lang reflect or java.lang class. You would then see calls to something like .new instance if they had like a reference to a constructor, or .for name if they're using the class format. The behavior for that doesn't really, it's not really defined because you're basically doing reflection to do some other technique, just not statically. JNI/NDK. If you see that being used from Android, you're going to see something called JNI exports. If you open up that native library within something like Girdra, then those JNI exports will just pop right up. You don't technically have to define JNI exports though, and so what you might see malware do is they will dynamically define their exports using a function found within one of the NDK libraries known as registered natives. Or sorry, it's actually in the JNI libraries. My bad. And registered natives will basically define those functions that you could then call into from Java. Once again, that's kind of just a general technique used to hide stack behavior, so it's not really clear what the behavior would be there. But again, please try to keep that in mind. DCL or dynamic code loading statically would use something called a class loader, path class loader, or dex class loader. There's also another I didn't list here called in memory dex class loader. And dynamically, you would simply see a new instance of one of those objects. The behavior is you might see a dropped dex file either somewhere in the file system in the app or possibly even the dex file within memory. And the reason for that is because you need that to actually load those dex files using these objects. For the execution guardrails, I'm not going to list too many, but just as one example, I'm going to talk about SimInfo. So statically, you'd see Telephony Manager being used. You might also see something like read phone state as a permission defined in the Android manifest. And if you wanted to hook it dynamically, you'd look for a call to get network or get country networks ISO or other methods implemented by Telephony Manager. And the behavior you might see from a cloaking guardrail technique like this is that if you change to be or if you change what like country that this function returns from, you might see different behavior in different countries. So as a quick example, say you're a phishing app and I run you in the US and you're a calculator app, but then I change my SIM country to Germany and all of a sudden you're a bank login. That's an execution guardrail. All right, so we've talked about techniques. Now we actually need to get into reverse engineering. We're almost there. So let's talk about what tools you need to reverse engineer. The most important one is going to be known as JDEX. And if you're watching this video, I hope you know what that is because we're going to be spending a lot of time in that. If not, download it now. Less known tools that you might need is going to be known as cyber or is some sort of method to take what you find in stack analysis and perform some sort of function, i.e., decrypt it. To do that, you could either do it in CyberChef or a scripting language, something like Python. I recommend actually knowing both of these because both are useful in their own unique ways. CyberChef is very quick to use, but doesn't do everything, so we might have to whip out a scripting language. Kotlin is not a scripting language, but it can actually be really useful to use Kotlin because Kotlin is how you write an Android app. So if there is an Android API you need, you can simply make an Android app using Kotlin to then test whatever technique you're trying to test. Beyond CyberChef for scripting, you also want Android Studio. That is, of course, the development IDE based on IntelliJ IDEA. Android Studio is going to contain things like ADB, the build tools, things like DX as well. It'll also, probably most importantly, contain the files needed to run an Android emulator or AVD. And you will want an Android emulator because if you don't have a test environment, you have to run your samples somewhere. Android emulators are pretty safe, so don't worry too much. But of course, you should be performing best practices when you're reverse engineering a malicious sample. I recommend having a text editor as well. Something like VS Code will do the trick. If you want to use something like Notepad++, that's fine. Doesn't matter too much. Just pick your favorite. You'll also want some form of hex editor. 010 is my favorite, but if you like IM Hex or don't want to buy 010, then IM Hex is perfectly sufficient. Again, just use whatever your favorite is. And that's basically it. That's with these tools here, you can reverse a lot of Android apps. But just to provide max coverage, let's talk about some other stuff. So, if you want to do more dynamic analysis, you are going to want an MITM interception tool. My favorite is MITM proxy, but if you like Burp Suite or HTTP Toolkit, feel free to use those. If you've never heard of this, then just use MITM proxy because it's open source and free. Frida is allows you to dynamically hook certain methods within an Android app. It's a very, very powerful tool. I'm not going to talk about too much now, but I have reversed a lot of malware using only Frida. If you can, I know we set up an ABD back here, but if you can root it, that's preferred and also required if you want to do MITM interception, because you're going to have to add your certificate to the system CA store. If you want to root something, I recommend keeping it as a production build, not a user debug build. And what that basically means is you want a factory image, which means you have to use something like Magisk or Kernel Sue. I recommend Kernel Sue simply because it's harder to detect. Next, nice to have tool is simply going to be Gearja or IDA Pro. That's going to be to reverse your native stuff. And of course, other tools. There's a lot of cybersecurity tools out there. I wouldn't try to learn them all, but always just be ready to learn. I did add Radar 2 here, aka R2. It's has some cool Android reversing features. I don't necessarily like it because I like to run my tools directly, but if you like that kind of environment, there it is. A similar story with Medusa. So Medusa is basically a very heavy Frida that contains a lot of built-in features. I find that what it does sometimes doesn't work or causes the app to crash or is just detected. So I like just to use Frida directly. But if you want to use Medusa, then feel free. Another tool that's probably very expensive is Virus Total. So if you have Virus Total Enterprise, you can like run your own YAR or snort rules, and you could start detecting APKs that way. You can also just use it to download samples. Uh, Lots of information can be had from Virus Total, but if you don't have Virus Total Enterprise, it's quite limited. All right, next up. Uh, that's going to summarize the crash course content for this video. Next, we're going to talk about or showcase reversing an Android app and using what we just learned. But if you want some more resources, I highly recommend the Android Malware Handbook. This goes into a lot of what I do actually, has lots of notes on detection. It's a very good read. I would also recommend giving a glance to the OWASP mobile application security framework that will contain a lot of like vulnerabilities that you might see in application. And those don't really mean much for a reverse engineer standpoint, but I think it's nice context to have. Laurie Wired, if you want, is a nice YouTuber. I think I spelled that wrong. Um, they do a lot of deep dives into applications. This here, Android App Reverse Engineering 101, is a dated but still quite useful introduction to reverse engineering. If you want something a little bit more slower pace, there you go. Next up would be the actual Android developer documentation. That's going to be very useful when you run into something that you don't understand. And likewise, the Android open source project source code itself. Don't just like mindlessly navigate the AOSP, but if you find some feature that you don't know how it works and it's not documented, then feel free to dive deep into AOSP. All right, that's it. So next up, we're actually going to look at our sample. So the sample we have is going to demonstrate all four of these samples that I have the X mark on. It is a sample I built specifically for this video. And the reason I did that is because I wanted to give something that people can practice with without actually worrying about it being malicious. So it demonstrates malicious techniques, but doesn't actually have any real execution. It's completely harmless, at least as long as my repository is good. It's on GitHub. The source code is there, so feel free to explore that, but don't use the source code to just jump to the answer. The key component of this app is it's made in the CTF format. So once you reverse all the malicious techniques, you can then reverse what the CTF is. I'm not going to show what the CTF is, but I'll get very close. I'll leave that as an exercise to you. Of note, this app is made in Jetpack Compose. So if you have reversed a few Android apps and they were XML based, this app might be a little complicated. And the reason I pick this app first is because I think this app is really good at demonstrating how you should use these techniques to determine what an application does without actually having to dive deep into every corner of the application. And that kind of leads to the first note, which is you should always go wide, right? Try to gather as much information as you can about the app before you start diving deep into every little behavior. You as a Android RE need to maximize your time use effectively to reduce the most user harm, and you're not going to do that by reversing some generic UI code. So always be searching for these common malicious behaviors and techniques. All right, with that, let's begin. If you want to follow along, you'll go to the GitHub page. Here it is. You'll go to releases and you'll download the app release ctf.apk. You then simply run it. There's also some hints down here if you want to start and link to JADEX. You can actually reverse this 100% statically. You don't need to run it in an emulator, but if you want to, feel free. All right, let's start. So I'm going to switch to JADEX. Boop. So this is JADEX. Hopefully you haven't seen it already. I have the main activity list here. You see all your decompiled sources on the left and any resources within the app, including assets, the signature, manifest, and other resources you might find in resources.asrc. But the first thing you should focus on is the actual Android manifest. This is used to define the application. So it's the first thing you should look at to try to determine what the behavior is. And the first thing you should be doing in the manifest itself is looking at permissions. So in this case, the app has internet and read phone state permissions. Those aren't that suspicious. Read phone state basically allows you to get some extra SIM information, but it's actually quite common. Many SDKs to clear it, so seeing this is not terribly unusual. This permission is simply generated, so ignore it. Next up, you'll have the application declaration. So this declares the app like process class. So this would be um, created and on create called when the process first starts. In practice, so that only happens when activity is being started. So up next is of course the activity. One of the activities will typically be called the main launcher activity. Technically, you can have an Android app without this, but when you click on the app icon on your home screen, aka the launcher, this is the activity that would be called and what would be called for on create. If we go here, we would see the actual entry point to the application. You'd also have the application entry point itself, which is here. If I can get to it, there it is. And many times you can actually find malware within one of these entry points. And in this case, though, since it's composed, that might be hard to do. And you can dive deep into these, but probably not going to find anything this time. In main activity, we see the application is built using Compose. We see it because we see the composable Lambda. You may not always see that if it's minified, but if you're seeing this weird pattern where you have set content and a bunch of code, that's typically going to be a Compose app. And the way Compose is going to work is it's going to sort everything into these Lambda instances or other Lambdas that are referenced like this. um, and to go deeper, you'll actually have to know how to reverse a pattern that R8 creates, known as R8 Lambda groups. That's what this is. So this is like the actual Lambda function being passed into this. Lambda groups work by having an integer value to define which lambda it is within a giant switch statement. So it's basically grouping several lambdas together, right? And then pushing them all into the same class and using an integer to define which implementation it uses. It's a minor optimization to compose. Unfortunately for us reverse engineers, it makes things a little confusing. So just to showcase the first example, I'm just going to close some of these tabs quick. This has the lambda ID of 1, so we know that this would be called default because the other one's 0. And typically with compose, you'll just see another lambda call. So we can see it's calling the same class except 0, so we'd go up here. This time we see a call to com.bumptech.glide.d.g. Go. And this is where the application gets a little tricky. Um, I mean, we could go into these classes here, like this one maybe, and we see a nav host controller, right? We see this, but now we're lost. I don't know where I'm going anymore. I'm clicking things that's not working. Boop, boop. This is likely where the nav graph of the app is, but I can't really figure out what's going on here. I'm lost. Oh no. This is actually leading into the first lesson. It's very, very easy to get lost. Now, I'll fully admit I reversed this beforehand, so I know how to get to the malicious code, but it wasn't where we just went. Um, you could spend hours going through this and find nothing. So, how do we avoid that? Well, let's go back to our slides. Remember, we made this table. So, let's look for something interesting. Let's look for base64. So, now I'm going to go back to JDEX and perform a text search. You can also do class search, but I just like to use the text search. And I'm simply going to look for class dot, or sorry, base64 dot decode, right? Just like this. And we see something here. Okay. We'll double click it to go there. And we see this. So what is this doing? Well, we see OK HTTP. So OK HTTP is something to do with making requests. It's a common library. We also see retrofit down here, which shows that this is likely a retrofit interface. In fact, we can see an interface here. So retrofit interfaces basically define the get and put in post requests of an you know uh, domain based on the URL you provided. And so this is definitely a URL. Let's take this into CyberChef. And we switch to sides. There we go. From base64. And we see it's raw.github-user-content.com. It's the same GitHub site we're just at. Oh no. And we can use this to actually build a complete C2. Now it's perfectly safe, so I'm simply gonna build the complete C2 based on that string we saw in the retrofit interface, which is this. We're just gonna visit there. It's not malicious, so we're good. And what do we see here? Well, we see a bunch of garbage. More base64 stuff. So let's copy this back in. Boop, boop. Huh. Well, that's not text. We could do something like detect file type. Nothing. How about entropy? Remember the behavior. High entropy content. So whatever this is has very high entropy. That tends to mean it's encrypted. In fact, it gives you a hint here. Properly encrypted or compressed state of a reasonable length should have a file or entropy of over 7.5, and it's probably not something like gunzip or something. I don't think the header is even matched. No. So we need to find the decryption key of this. We go back to JDEX, and we're not really seeing it somewhere here. Sometimes it might be possible to see like a decryption function here. We could find the usage of this maybe. I keep, well, JDEX won't let me right click. Oh, there we go. And that just leads us here. Okay, object. Okay. What is this? Well, going back to our handy dandy slides, do final javax.crypto.cipher. We can see that this is executing do final. And although it's not, you can't see the javax.crypto part, we see the cipher. So immediately after this is called, right here, it is then decrypting it. We can see that it's base64 decoding the object. It's kind of doing a wacky way of getting there, but there it is. And then making a secret key spec with panda panda panda, A. Initializing a cipher, that is AES, the Advanced Encryption Standard, CBC, cipher blockchaining, PKCS5. padding. It then declares an IV, once again, panda, 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 A. It's not that uncommon that these would actually match. It then initializes a cipher with a secret key spec in decrypt mode and gives the IV, and then does a do final on whatever dot B is. Or sorry, whatever this is, which is probably the base 64 we were just looking at. So let's take this information back to CyberShift. Boop, boop. You go to CyberShift, go to AES decrypt. You'll typically just select CBC no padding. The algorithm we had padding, but since we're decrypting, that padding should already be there. That might be important because CyberShift doesn't actually support all the correct padding. I think it does PKCS7, I want to say. We'll change this to UTF, change this to UTF, change this to raw, and this to raw. We do detect file type. And we see it's a DEX. Okay, so Dalvik executable as used by Android. Well, that's interesting. What do we know utilizes DEXs? We know that DCL might utilize a DEX. So we might see a drop DEX file or DEX file in memory. In this case, we basically statically replicate those steps, but if we were running it dynamically, that's what we would see. And we should see a reference to something like DEX or PAF class loader. So let's look for those. Find my search box back. First, let's search for DEX class loader. And base DEX class loader, base DEX class. These are not the class loaders I'm looking for. Let's search for PAF DEX class loader. And I got nothing. There's also another one called in-memory DEX class loader. And I once again have nothing. Why is that? Well, what do we know that can hide a call to class loader? Well, specifically class loader new instance. Reflection. Reflection can cause this. So let's look for that. I like using class at for name. You can use constructor at new instance. There's various things to look for, but let's look for class at for name. Flash dot for name, just like that. We get quite a bit. So based on what we know, by searching for path dex class, path class loader and dex class loader using text, we didn't find it. So whatever's past the class that for name is probably not an SDK, and it's probably not, defined. So let's look for something matching those conditions. And here we see something matching those conditions. In fact, this here looks interesting. Class at for name, let's get constructor. So let's go there. What is this? Interesting. This is a very complicated object. We see it getting a view model. It's collecting a state, so a composed state. Checking telephony manager. Ooh, get network country ISO. It's checking if the telephony manager is Singapore, specifically to get network country ISO. And based on that, it's doing something. It even says DEX payload. So it's making a file called avocado. It's reaching into this, whatever that is. There's a list here. And then whatever list.get0 is. Well, what is list.get0? It's coming from something called the DEX payload. Well, I mean, obviously we know it's a DEX file, but where is this coming from? Let's look for some usage here. Maybe, no, that's not useful. Look for maybe a different one like this. Oh, we've been here before. So this class was made after we did the decryption. It's invoking some sort of function, whatever that might be. It's not important to reverse it, but it was declared in dis.c, so it was passed somewhere. Oh, sorry. Function one, dis.c. Where's dis.c? Must be set somewhere else. Might be SDK code. Might be. Anyway, we know it's initialized here, and that was the only initialization we saw, so it must correspond to what we saw being decrypted here. And this list 2 seems to be something else within that same payload, so let's go back to that weird implementation we found. And let's also go and look at the weird stuff. Burp. Huh. We see a list up here. And in that list, we see dalek.system.path class loader. So, as a mechanism to obfuscate strings, this application, instead of having the strings just here or encrypted somewhere, decides to remotely get them. And based on that, it does everything it needs to call path class loader. It gets a new instance of it, construct that new instance, which would actually perform the loading of whatever we put in. Oh, sorry. Find that back. The Foster. Which ends up being this file called avocado, and it's writing the bytes that we just decrypted. All right. What does it do with that? Well, it does some housekeeping. This is basically adding it to the path list of this class loader, and then starting an activity with string. String is list.get2. That was com.jinx.main activity. Okay, well, we saw that before. We saw that in the Android manifest. And in fact, if we try to go here, we can't get there. In fact, we can't get here either. Whatever is com.jinx, it's not in the APK. So it must be within this DEX. I wonder what the DEX does. That is where I am going to leave my analysis at this APK. If you want to figure out what the DEX does, you're going to have to replicate my steps or find a different way to figure it out. But what did we learn here? Well, we learned that the app is making a call to this GitHub base C2. It is decrypting this garbage and then loading that into its application here using path dex class loader. It then calls an activity, or starts an activity, I should say, called com.jinx.main activity. That is the definitive example of DCL, and it is many times used by malware. And in fact, if you're a expert reverse engineer, there's probably some red flags going off right now. And maybe in the future you'll learn why, but this is a common pattern for a certain well-known family of malware. But that is where I'll leave it here. Again, to reiterate the tips, use techniques to find the behavior. We spent a lot of time just navigating mindlessly through Compose, but we might have never even gone anywhere. Now we know that this is the malicious class, but we could have very easily gone somewhere else. We could have gone down here and into this. If we can even get JDEX to behave, I don't even know where we're at anymore. This SDK code is very easy to get lost. But if you stick to the techniques, you can reverse these apps. More importantly, you can do so quickly and effectively. That is all I have for now for this video. Best of luck in your future malware reversing endeavors. Thank you.